Hello, everyone. I'd like to welcome you all to this this term's instance of this course is officially either 15213 from computer science or 18213 from electrical and computer engineering. But a large number of the people enrolled in this course are in one called 513, which is for graduate students. And to be totally honest, you're not supposed to be here because you're supposed to watch the videos, the lectures by video later, but we're not checking any cards, so I don't really know who you are. Anyways, this course is, as you can see, a very popular course on campus. We have over 600, shouldn't exaggerate, students on campus enrolled in one of those three versions of the course, which if you think about a university of the size of CMU, that's like about 5% of the total student population. So we're very glad to have you here. And this gain is too high. I think we overdid the gain. Try that, that's better. So my name is Randy Bryant, and my co-instructor is Dave O'Halloran, and those names might be familiar if you have been to the bookstore, because the book was written by us. And we actually wrote this book. We started 213 as a course in 1998. And I know that you were children then and all that stuff. But out of response for a new type of course that you'll see today that sort of gives people an in-depth understanding of systems, but more from a high level or programmer's perspective. And we'll talk some about the philosophy of the course later. So this book, as you saw, just came out its third edition last March, and that's the required text for the course. And there is nothing you can do to avoid buying that book. And it's not because we're greedy. Actually, we take the money we get from royalty for students in this course, or any CMU course, and we donate it to CMU. So we're not actually making any money out of you buying the book, but it's a simple reality that the new version is different than the old. We expect you to be using the new version. There are no electronic copies. There are no pirated versions, so you basically have to buy the book. And I don't really apologize for that because I know you or your parents or somebody's paying a lot of money for you to be here, and so the price of the book is really a relatively small amount relative to that. And this course, by the way, is not, some courses there's, oh yeah, this book, you might want to look at it once in a while, but actually the course has nothing to do with it. This course, the book and the course are one. They're very tied together. There'll be parts of the book that we don't go into all the details that are in the book sometimes, but we expect you to be able to figure it out. And so really the course and the book are tied together, and they very much, the progress of the course, the topics covered, how it's covered, everything about it is consistent with the book. And we wrote the book because of the course. Think of them as course notes. So, and the reason why we are teaching this term, by the way, we haven't taught together in several years, but because this is the first rollout of this book, and not only is it being used here, but it's actually used by about 250 schools around the world, and many of those people are also going through the same activities of teaching from this new edition for the first time. And so we wanted to make sure all the material for the course was sort of put in order and things, because other universities and other colleges use this material, the supporting material we've developed. So that's the course. And today is the first lecture. We're sort of doing a tag team here. I'll talk the high level, what the course is about, what the main themes are, and Dave will talk more about the logistics. So we refer, the saying we have, when the very first time I typed the number of this course into a text editor, I realized I've typed those 5 digits many times in my career because it's the zip code of CMU, 15213. So that's where we come up with the saying. So there's a few things about this course. For the most part, you know, in your normal undergraduate curriculum, when you've learned programming, you've been very much separated from the realities of the machine. You just think about code, you put some text into some little box somehow, and out comes a behavior that it hopefully is what you intended the program to do. The purpose of this course is to give you enough understanding of what that box is doing when it executes your code. And through that, to help you become better at what you're trying to do. So some of the outcomes is, there's really 2 types of outcomes from this course. One is that if this is the only systems course you ever take in your whole life, you will get useful material from it. You will learn tools, tricks, methods that will help you if you ever are involved in software development, large-scale software engineering projects, systems, hardware design, any aspect of computer technology. This will help you be better at what you do. You'll understand what programs do, how they work, what the machines that support them do, why sometimes they work really well and why sometimes they don't work so well. It also is intended as a sort of stepping stone into a whole number of other courses at CMU that will give you more in-depth understanding of computer technology, but are sort of specialized by topical area, whether it's computer networking or operating systems or embedded systems, where you'll take the sort of ideas from this course and be able to then learn in a somewhat narrower but deeper sense what's really going on. And so it really is trying to serve those 2 goals of making you more effective, giving you useful ideas and tools right away, but also preparing you for later courses. So one way we talk about this is sort of what kind of stuff will you learn from this course is to go through a series of what we call great realities, places where sort of computers meet up, real live computers meet up against your expectations, and maybe they're not quite the same. So one of them is, and the first part of the course is going to take a fairly detailed look at how numbers are represented in computers, and you'll learn some things that are on one hand surprising and on another hand will start to make sense when you understand it better. So a simple case is for numbers. I don't know when it was, but it was probably in about 8th grade algebra that I learned that if you square a number, it will be at least 0 if it's not an imaginary number. So either an integer or a real number, you'd expect to square it and it to be a positive value or perhaps 0, right? And that's actually generally true with floats, or representation of floating point numbers. But with integers, or ints, you know, the computer representation of integers, it's not so clear. So, for example, if you square 40,000 on most computers, then you'll get whatever that should be, as you'd expect. But what if you square 50,000? So you could do this in your head, but I actually built into this laptop is a computer, so I'm going to go ahead and use it. Let me just size this a little better for you here. Oops. And use a tool which on Unix systems is called, no, it's going on. This is working before. Let's try again. Here we are. On Linux systems, it's called GDB, but on a Macintosh OS X, it's called LLDB, but they're pretty much the same program. You will get to know this program really, really well this term. So like I said, if you square 40,000, you'll get what you'd expect. But let's change this to 50,000. And you get a very peculiar number that doesn't look anything like you'd expect 50,000 squared to be. And in fact, it's negative. And so that might just seem like, well, there must be a mistake or something. No, that's just the way it is, because this computer is expecting numbers to be represented as 32-bit values. And the bit pattern that you get when you do this multiplication happens to be the representation of a negative number. So that's an example of where your normal expectations about integer arithmetic may or may not hold. On the other hand, there are some places like if I try to do the same thing, multiplying 300 by 400 by 500 by 600, then all of a sudden I also get a number that clearly is not what you'd expect, because the same thing has happened. I've gotten an overflow. It happens that it's overflowed to a value that's positive, not negative, but it still is obviously not the integer product of those four numbers. On the other hand, one thing you'll find is even though this arithmetic is not normal sort of integer arithmetic, it actually has some well-behaved properties. So for example, if you look at what I've done is I just moved the 300 around from the beginning of the product to the end of the product. And so now if you think about how associativity and commutativity works, I'm basically multiplying these four numbers in a different order. But what you see is you get the same funny-looking result no matter how you do it. So what you can say from this is integer arithmetic is commutative and associative. So it obeys some of the conventional mathematical properties. It just isn't what you'd expect it to be. It's not a normal sort of mathematical integer arithmetic. So the cartoon here shows an example that's a similar possibility. Let me get to it. Oh, I guess it comes at the end. So then the next question is addition associative, right? Can you order the numbers? And as you probably might have figured, both in the integer arithmetic, even though it has this potential for overflow, it is associative, and it's commutative too. But for floats, it's not really quite the same, because the range of values you can get in floating point are so extreme that some numbers kind of disappear on you. So the example I'll show without having to use a computer to do it is if you take a big number and subtract it from itself, you'll get 0. So if you add that to 3.14, you'll get 3.14. But if you take those two numbers and you reorder how you combine them so that 3.14 compared to minus 10 to the 20th is so insignificant that result gets turned into minus 10 to the 20th. And you add that to 10 to the 20th, and you end up with 0. So it's not associative. And so what you see is both these number systems have some peculiarities, and it all comes down to the fact that they use finite representations of things that are potentially infinite in their expanse. And so there's some compromises in how those work. And what the compromise is, you can overflow in integer and run out of room. And in floating point numbers, you have round-off problems where you sort of drop the digits that aren't significant. You can also overflow floating point, but the more common problem is round-off. So this is shown in this cartoon, this idea of overflow of somebody counting sheep which in the US is, or in English language at least, a way to fall asleep. And when he or she goes from 32,767 and then increments that by 1, gets minus 32,768. And we'll see exactly why that happens, but basically the numbers are going up to the largest value it can represent, and then when it goes one more, it becomes a negative number. So these are really important things to understand. I mean, 90% of the time, maybe you can just get by writing programs and not worrying about whether your numbers are going to exceed their possible range. But there's sometimes when this could be really important. If you're like controlling a rocket, you really don't want the positive thrust to become negative or something like that. So you can see this could be an important consideration. Similarly, there's well-known instances of security vulnerabilities where somebody wrote code that sort of expected a positive number in some place, and a clever person figured out if I supply a negative number, I can fool the system and get it to do bad things. So these are the kind of corner cases that you need to understand better if you're either working in programs where it's really, really important that it work correctly, or you're really worried about security vulnerabilities. Anytime you have possible for corner cases, you have to understand these nuances better. Similarly, for floating point, if you're going to use floating point for serious computation, whether it's scientific research or for designing bridges or nuclear power plants or something, you better understand what the characteristics are. So that's our first one, and we'll spend a couple of weeks talking about numbers and number representations and their properties here. The second is we're going to spend a lot of time in this course learning about machine-level programming, meaning what the instructions are that actually get executed by the computer. And that can be described in assembly language, which is a text version of it, or an object code, which is the actual bit-level binary encoding of instructions. And we'll learn a fair bit about that and spend a fair amount of time seeing how code that you write in C gets turned into machine code and how that gets executed on the machine. One thing I'll say is that historically, courses like this would teach assembly code by having you write programs in assembly that do various things, not usually very interesting because it's a lot of work to write an assembly program. This course is much more about taking the assembly code that's been generated by a compiler, a C compiler, and looking at it and understanding it. And that's a different set of skills than you need to write it on your own. And in particular, we're going to look at the language of Intel processors. The most recent versions of them are called x86-64, the 64-bit version of their instruction set. And one thing that's new in this course compared to previous ones, we used to teach 32-bit stuff. This course is 64 bits all the time. Another one that we'll talk about a fair amount and that is really fairly visible to programmers, surprisingly visible, is aspects of the memory system. So modern computers have a very complex layered memory system to try and give you high performance and high capacity at the same time. And there's some results of that system that can mean that if you write a program well, it might work really well. And if you don't, it could run very poorly because it's not making use of this hierarchical memory system. So, and also, there's a lot of bugs that show up, especially in C programs, that have to do with memory referencing errors. And so understanding what those errors are, what their manifestation is, how to prevent them is a big part of the course. So for example, if I define a struct that contains two integer values A in an array and a double precision floating point number D, and if I, this function fun, you'll see what it does is it's given an argument I, and it sets the ith element of A to some strange looking value. So as you know, I should really only be either 0 or 1 with this code, because that's the range of possible values of this array A. But we can try other things too. So in particular, if you run it on either 1 or 2, you'll get what you'd expect, that you assigned 3.14 to element D of this structure, and when you read it back, you get the same thing. And in fact, but now if I set A of 2 to this number, all of a sudden you'll see that my floating point number, which seems to have nothing to do with A, has changed. And if I do that same thing with I equal to 3, you'll see I get a number that's closer to 2 than to 3.14. And if I keep going, well, nothing much happens until I hit 6, and then the program crashes. So something interesting is going on here, at least something quirky is going on. And the reason is, again, it has to do with how data is laid out in memory and how it's accessed. And one of the features of C and C++ is it doesn't do any bounds checking on arrays. It will happily let you reference element number 5 million of a 2-element array and not complain, but the operating system might complain, as it did here. And in this particular structure, and we'll see more about how structures are implemented and laid out, but basically if each of these blocks in this vertical chain represents 4 bytes. And so the 2 elements of A each are 4 bytes. D is 8 bytes. And then there's some other stuff in the other beyond that that's not actually in the struct itself. So you'll see that if I reference either A of 0 or A of 1, then I will just modify that array as designed. But when I'm calling fun of 2 or fun of 3, what I'm actually doing is altering the bytes that encode this number D. And that's why you saw the sort of funny numbers come out of it. And as I go up, at some point when I hit 6, I'm modifying some state of the program that it's using to kind of keep things organized, most likely how it keeps track of allocated memory. And that's causing the program to crash. So this is a pretty good demonstration of why C programming can drive you crazy. Because as you saw, it doesn't do bounds checking. So it's easy to write code that does invalid stuff. It's also often the case that you'll cause some problem, and it has this sort of action at distance feature that you can modify think you're modifying some data structure, and what you're doing because of the way things are organized in memory, you're changing something totally unrelated somewhere else in the program. I mean, imagine they're not just 1 apart, but they're 10,000 apart. And things might just run fine for hours, days, or weeks, and then all of a sudden, at some point, that data that got corrupted a long time ago gets accessed, and something goes wrong. So this can be some of the worst debugging nightmares that exist on Earth, is to try and figure out memory referencing errors. So this is actually one argument not to program in C or C++, and it's a valid argument, I'll admit. But also, as a person who's writing a lot of C programming, you just get more experienced, and you know at times that you should actually put bounds checking in your own code. And there's also tools available that will help you sort of bulletproof your code so that it will detect these kind of problems. So it's not like you have to change languages, but it is a particular feature of these languages. And so understanding sort of the machine level representation of data structures and how they work really makes a huge difference in your ability to deal with these kind of vulnerabilities and things. Vulnerabilities, by the way, also from a security perspective. The the fourth sort of theme we'll cover in the course is getting performance out of programs. Other parts of the curriculum in CS do much more emphasis on getting the right algorithm or the right data structure. And that's really well and good. It's important stuff. I don't deny it. But there's some amount of the sort of low-level optimization that you need to do, that you need to understand what the system does, what makes it run well, what makes it run poorly, in order to be able to do that kind of optimization. So the example we like to use is these two functions do exactly the same thing in terms of their behavior. What they do is copy a matrix or an array from called source or SRC to a destination DST. They're both sized to be 2048 rows, 2048 columns, two-dimensional arrays. And you'll see that the programs do the obvious thing. You have a nested pair of loops to do the row and column indices, and you just copy from one source element to a destination element. The only thing that's different, you'll see, is that the two loops, their nesting is different. Their nesting order is different. In one case, I'm going kind of row first, going through all the rows, and then the columns, and the other is for any given row, I'm copying all the columns. That's really the only difference between these two programs. But what you'll find if you run it on a typical system is that one is much faster than the other. In this particular machine we ran it on, it was about close to 20 times difference in performance. So something fishy is going on if the same program that differs only in this seemingly insignificant way, a way that has no effect whatsoever on its functionality, can have this much performance difference. And so to understand this, you need to stare at the cover of the book. Because basically, you're at two different points of this strange-looking picture that's on your book, and since there's no axes or labels on it, it makes no sense whatsoever. But it's there. So what you see is this picture shows for different memory access patterns, and I won't go into the details, what the throughput measured in megabytes per second on basically a copying program was. And without going into the details, what you'll see is these two functions sort of sit at different points in this memory access pattern. The one that goes through row by row is much better than the one that goes through column by column. And as a result, you're getting a lot better performance, and it has to do with this memory hierarchy and what they call the cache memories, that you're getting way better performance out of it in one case than the other. So that explains what the cover of the book is about, and we'll talk about it more later in the course. And then a final part of the course talks more about not just getting computers to run little programs in isolation, but getting computers that talk to each other over networks and implement services like web servers and other functions like that, which of course is where most of the world of computing sits today. It's not just isolated machines, but computers that interact with each other over the network. They're embedded controllers that are interacting with the physical world. So really the world of computers is a much richer environment, and we'll cover at least some aspects of that in the final part of this course. So as I mentioned, the other feature of this course is it will get you ready for other systems courses you might take at CMU. And here we've listed actually a subset of the courses at the university that require this course as a prerequisite. And they're mostly in computer science and ECE. But you'll see it's quite a range of different courses. And each of them builds on sort of one or multiple aspects of the material you learn in the course. So the reason why we make everyone take this course, including incoming master's students, is that all these other courses at the university have come to rely on students being familiar and having done the work of 213 or 513 as a prerequisite. And they can build on that material and sort of cover more ground as a result rather than having to do what would otherwise be somewhat remedial work on it. And in fact, part of the genesis of this course was the people who taught the operating system course, 410, sort of complained that they were spending too much time at the beginning of the course talking about some very basics of machine programming. And Dave and I said, oh, well, we can cover that. So that was part of what got this course started. And as I mentioned, the course has a sort of perspective that's very different from traditional systems courses. Most systems courses, including that whole array you saw there, were about how do I build some particular feature? How do I implement an operating system? How do I design a pipeline microprocessor? That's all important stuff to know. We really want the people who are out there building operating systems and designing microprocessors to have learned how to do it. On the other hand, as a way to sort of get new into this and get the introduction and get the experience, we find it more useful to take what we call a programmer's perspective, meaning understanding what you as a person who sits in front of a computer screen and types code need to know about that machine you're typing code for in order to be effective at doing it, as opposed to somebody who's someday going to be designing the actual machine itself. So that by taking that perspective, it gives you sort of an understanding. So now when you go off to implement it, you'll actually know what these features are and why it's important to implement them well. But also, by doing this programmer's perspective, it lets you right away get tools that you can use in other places where you're writing programs or doing anything related to it, and be more effective at that. So this programmer's perspective really gives this dual benefit to it that we feel is very useful, and students who've taken the course in the past have expressed that as well. So as I mentioned, we have 2 instructors for the course, and they also happen to be authors, and the longest, we've probably taught this course more than anyone else, but it's also taught by other people on campus as well. So what I'm going to do now is hand my pair of microphones over to Dave.
All right, welcome. Good afternoon. It's great to see you. My name is Dave O'Halloran, and I'm just delighted to have the opportunity to be one of your instructors this term. This course is one of the reason I'm so excited to be teaching this course. I mean, I just love this course, and the real reason is the opportunity it represents to have an impact on people's lives. We really believe that the material you learn this semester can have a really positive and long-lasting impact on your careers. And it'll help you not only with your future classes, but also future positions you have. And I hear this from people all the time, former CMU students and students around the world who have taken the equivalent of 213 at their schools. I even, a couple years ago, we were interviewing a faculty member, a tenure track faculty member, who did his undergrad at CMU, and then went off to Stanford, got his PhD at Stanford, and was coming back to join the faculty. And he told me that 213 changed his life in our interview. Now, I don't know if he was trying to butter me up, but I think I believe him. He said it changed his whole life in the sense that it gave him a research direction. He didn't really know he knew he kind of liked computer science, but he didn't really know what direction to go. And after he took 213, he knew that he wanted to do his life's work in systems. Now, it was just remarkable, right, to come back, and we ended up actually hiring him. And he told me that everybody in his lab at Stanford, all of the grad students, had a copy of the book on their desk. And they were from all over, all different schools. And so, I mean, I was in a bookstore in Beijing a couple years ago, right outside the PKU campus. And I was up on the 5th floor trying to see if I could find a copy of the textbook. And I found the English version in one aisle. And then a couple aisles over, I found the Chinese version. I was going through the Chinese version, and this guy taps me on my shoulder. And I turn around, he says, "Oh man, that book is really good. You should, the English version is 2 aisles over." And I mean, it just blew me away to be in the head of someone like halfway around the world. It was just one of those moments. And so I'm not trying to boast. I'm just trying. What I want to give you the sense of what an opportunity this course represents for Randy and I to have what we hope will be a really positive impact on your lives. So let me. We have kind of a funny organization for the course in response to the tremendous demand we found that we have for it. So there's actually 3 course numbers, but it's all the same course. Okay, it's the identical course. 513 is for our master's students, and the 513 doesn't have a formal lecture, so there's no seats assigned to it. Instead, we'll videotape the lectures, and we'll make those available on the course web page for our graduate students. And the reason we do this is just because in the past, we didn't have enough seats for everyone, and there would be cases where there might be 100 or 150 master's students on the wait list. They wouldn't be able to get into the course. And we didn't really want that because they need this course to take other courses. So that's the reason why we have this sort of does not meet version of 213 and 513, because we can admit all the master's students that need to take the course. Now, 15213 and 18213 are for undergraduates in computer science and ECE, respectively. Okay, and the undergraduates will go to lectures and recitations, okay, in person. Graduate students will watch videotapes of those. But otherwise, yes?
For those videotapes, will they be available to all students, including undergrads?
Yeah, we're making them available to everyone, actually.
And lecture slides as well?
Sorry?
And lecture slides as well?
And lecture slides as well. Everything's available on the course webpage. So you'll be doing all of students will have equal access to office hours, the staff mailing list, and everybody does the same labs and the same exams. Okay, so it's just a matter of whether you go to lecture in person or if you watch it on video. In fact, if since it's available to everybody, if you miss lecture, it'll be there on the webpage and you can catch up, which I know you'll probably do. Actually, I know most of you will never miss class, right? But the few of you who do, you'll be able to watch the video. Okay. All right, this is the one part. This is the part I hate. I love teaching, but this is the one part of teaching that none of us really like, but we have to talk about it, and that's academic integrity. If you're new on campus, coming from an international school, if you're an international student, new on campus, there might be different notions of academic integrity and different notions of cheating at your undergraduate school, or your old school. So if you're new on campus, pay very close attention to this, because at Carnegie Mellon, we take academic integrity very seriously. Okay, it's not a wink, wink, nod, nod. We're very serious about it, and we want everybody doing their own work to preserve the integrity of the courses. So what exactly is cheating? So if you share code with anybody, either copying, retyping, looking at somebody's code, like if you look at somebody's code on the screen, or if you give somebody a file, all of those examples of sharing are cheating. If you describe your code like line by line to somebody, that's cheating. If you coach somebody line by line, that's cheating. Okay. Searching the web for solutions, just the act of searching is cheating. Right? And this is a real problem for us in particular because the course is offered all around the world, and people either maliciously or sometimes just they're proud of their work and they post it, for employers on like public GitHub sites. So it might be tempting to search for these solutions, but even the act of searching is cheating. And definitely, if you find a solution and use it, that's cheating, even if you modify it afterwards. And I just want you to remember, I know how to use Google just as well as anybody else, right? So I can search for solutions too. Copying code, you might be tempted to copy code from someone who took the class, in a previous semester. Don't do it. That's cheating too. Now, what's not cheating? So you can help each other use tools. If somebody's having trouble using GDB, or they have questions about how to use a text editor, that stuff's all great. You help each other out using the tools, how to log into Shark machines, all of that kind of stuff. And you can discuss sort of high-level design issues, and that's probably a good idea. Yes?
I use my own code from a previous course.
Yeah, yes. Did you take it a previous semester?
Yes, I dropped it for some reason, but I just did
Okay.
do that.
Okay, yeah, the question was, if you took it in a previous semester, can you use your work? And the answer is yes. So you can also talk to each other about high-level, design issues. How are you using an explicit list? Are you using a segregated list for your Malloc lab? Okay, that kind of stuff is okay. Okay, high level, okay. Low level, not okay. And basically, we want you to write your own code. This is not, it's kind of a cut and paste world these days, right? You look stuff up on Google, Stack Overflow, you cut and paste it. But that's not the way we do it here. We want you to do the work yourself. We want you to enjoy the experience of figuring things out and learning how to solve problems. Now, the consequences for cheating, there's a single sanction. If you're caught cheating, you'll be expelled from the course with an R. There's no exceptions. If you drop the course, we'll just reinstate you and then flunk you. It's really, it's a very serious penalty because we just take it so seriously, and it's just something we don't want you to do. We have amazing tools to detect code plagiarism. We have amazing tools to detect plagiarism that are resilient to renaming, reformatting. They operate at a very deep syntactic level. And so just please, don't do it. We have, I think, 18 TAs. We'll have office hours almost every day of the week. There's plenty of opportunities and ways to get help. Start early. If you get stuck, start early enough so that if you get stuck, you can go ask for help. We have automatic extensions built in if you need more time. I'll talk about that later, form of grace days. But please, whatever you do, don't cheat. It's just tragic when it happens. Last fall, 25 students were expelled from the course Some were expelled from the university because it was a second offense. Many were sent home. I talked to students who were like the only person in their family to go to college, the only person in their village to go to college, and they were going home without a degree. And it's just tragic. It's just, so please, please, please don't do it. Do your own work, and it'll be a wonderful experience. Okay, as Randy mentioned, the textbook is Computer Systems: A Programmer's Perspective, 3rd edition. You can, there's a whole bunch of supporting material on the book's website at csapp.cs.cmu.edu. And as Randy mentioned, this book really matters for the course because actually the book came out of the course, right? So the book is the course is the book. And so it'll really help you. The labs that we do come directly from material that we discuss in the book. So what I would encourage all of you to do, and I'm not sure if anybody has ever taken this advice, but I say it every year anyway, because I believe it. But I think a really good strategy for studying and preparing for this course would be to read each chapter 3 times. Okay, read it 3 times. Work the practice problems. So we have littered throughout the book are practice problems with solutions at the end of the chapter. And these practice problems are like little sort of bite-sized morsels just to kind of check your, kind of a sanity check of your understanding of the material. So I think if you read the book each chapter 3 times and worked the practice problems, that would be an excellent way to go through the semester and prepare. The other book we use is the Kernighan and Ritchie's classic C programming book. I think this was written a long time ago. It's still the best book around, I think, for C. It's a beautiful example of technical writing. It was one of the inspirations I used when I was writing the book. You know, I tried to find that same clarity and precision that Kernighan and Ritchie have in their book. And so this is a really good book. I mean, this is the kind of book, it's a reference, but it's the kind of book you can just read from beginning to end and get a really good understanding of C. There's 4 main components to the course. There's lectures where we go over the high-level concepts, recitations which meet once a week for an hour, led by a TA. And the purpose of the recitations is really to help you with the labs. Right? So it's very practical and hands-on. There's 7 of those labs, and these are really the heart and soul of the course. This is where all the real learning comes in, I think, when you actually have to do this stuff. And that's why we take the cheating part so seriously, because if you do these labs, you're going to learn an incredible amount of really cool stuff. If you don't do them, you won't learn anything. Right? So each one of these labs is 1 or 2 weeks each, and involves typically some kind of programming or measurement. There's also 2 exams, a midterm and a final. The exams are proctored. They're online, proctored in Wien and Gates. And what we do for the exams is we take 4 days from 10 to 10, and then you can sign up. And then we have multiple clusters that are network isolated, and then you can sign up for a slot, like a 6-hour slot. And the midterm is nominally an hour, 80-minute exam, right? It's the same exam we gave when we used to have people sitting in person. So it's nominally 80 minutes, but we give you a 5 or 6 hour window to do it. Okay, so so you can sign up anytime, any day that there's a slot. Okay, so there's flexibility, so you can kind of tailor it to your schedule. And I think we've also removed all the time pressure, right? So which is, you can go back, you can check your work, you can just kind of relax and not be worried about how quickly you do it. Now, there's many different ways to get help. The main source of information is the course webpage. That's www.cscmu.edu/213. And all of the information is there. We've got a complete schedule of lectures and assignments. We don't change it. It's fixed. And so you can look at that and plan your semester knowing that those dates won't change. We've actually even got all of the lectures posted ahead of time for the other instructors around the world who are using the book, so we needed to get them all ready. There's also news at the very beginning. There's sort of news. If we need to make announcements, we'll post it there. We don't use either Blackboard or Piazza in the course. Instead, we have a staff mailing list that you can send mail to if you have questions. And all of the TAs and all of the faculty are subscribed to that staff mailing list, and so we'll all see it. And we try to have really fast feedback. Right? So there's so many people looking at your emails that chances are very high you'll get an answer back quickly. The disadvantage of having this the advantage of this mailing list is that it allows us to control the message and control what feedback we're giving back to you. The disadvantage is that we often get the same question over and over again. And so for that, we've established a FAQ. If we find we're getting the same questions over and over, we've established a FAQ on the course webpage for sort of organized by labs. Okay, so you can see the answers to frequently asked questions on there. We have office hours. I think we're still trying to meet with the staff and figure out the exact office hours. But what we're thinking now is that we'll have office hours 6 days a week. Okay, every day but Saturday. They will be at the same time and same place every day. So from 5:45 to 8:30 in Wien, the Wien 5207 cluster, we'll have 213 TAs there to help to answer your questions. Okay. So you don't have to make appointments. I mean, you can make an appointment to see any staff member, of course. But you know that at the same time, same place every day, there's somebody you can go to for help. Right? Okay, for our labs and exams, every lab is a single person, so we don't have any group projects. Okay. We want you to do the work yourself. Now, it's important to work in groups, and you will learn how to work in groups in other classes. CS classes, but not in 213. This is a kind of a core course. We want you to figure stuff out yourself. All of our hand-ins will be due at 11:59 p.m. on either a Tuesday or a Thursday, and this is, you can see which on the schedule page, on the course webpage. And all of our hand-ins are using Autolab, where you've probably used it for some of your other classes, but it's a auto-grading service that allows you to get instant feedback on your hand-in. So when you hand it in, you get feedback right away. The exams, like I mentioned, are going to be in network-isolated clusters held over multiple days, and you can just sign up for a slot that's available. Now, what usually happens, if we offer like the exam Tuesday, Wednesday, and Thursday, the Thursday slots fill up immediately. And so, I guess you should try to sign up soon if you want. But people always seem to want to defer to the end rather than. If it was me, I'd want to get it over with. But so that is sort of a constraint, right? That if you can only sign up for slots that are available. Okay, now, we make mistakes. We always make mistakes, especially with just so many students. So there's a specific process for appealing grades if you think that that your work wasn't graded properly. So what you do after either an exam or after your labs are graded, You have 7 days to file an appeal, and appeals have to be in writing and hard copy. Okay, so there's no, we won't consider any appeals via email. It has to be in writing and hard copy, and you give those to me. And if I'm not there, you can just slide it under the desk. Okay. And the reason we do it that way is it allows us to treat everybody fairly. So we get all the appeals together at once, and then we can treat everybody the same way rather than just sort of doing them one at a time like that. Okay. Now for our labs, we have 10 machines that were donated by Intel called the Shark machines. So initially, our first version of 213, I guess we started using Intel machines in 1999. We used Alpha processors for the first year. I like to fish, so all of our machines were called the fish machines, right? They were freshwater fish. And then we upgraded a few years after that, and those were the saltwater fish machines. And then we upgraded, like in 2011, to these Nehalem class servers. I'd run out of freshwater fish and saltwater fish, so the next grade up was sharks, right? So every fish is named after some kind of shark. But these are the same machines that Autolab uses for grading, right? So there's some consistency for performance-oriented labs like Malik Lab. And you can access them. The names are listed on the course webpage, and so you can SSH to a specific machine. They're all identical. If you have an Andrew account, you've already got accounts on the machines, right? So there's nothing special to do. Or you can just SSH to shark.ics, and it'll just randomly put you on one of the Shark machines. Okay, if you have any trouble logging in, just send mail to the staff mailing list. Okay, we know that during the semester things come up. Grandparents die, especially near the final. That's harsh, I know. But things come up, right? And you're very busy, you're taking a lot of courses. So instead of sort of dealing with requests for extensions and all these special cases, what we do is we give you 5 grace days that you can then spend as you wish. So if you hand your work in late, 1 day late, you'll automatically consume a grace day. Okay, we don't allow you to sort of allocate the grace days. You spend one of your grace days by handing in late. So if you have a grace day left and you hand in late, you'll spend that grace day, but you won't be penalized for the late hand-in. And so we have 5 grace days over the entire semester, and a maximum of 2 grace days for the assignments. Now, we're going to set up, since the first 3 assignments are kind of not as programming intensive and don't take as much time, we're not going to allow any grace days for those because, 1 grace day, 1 grace day. And then for the latter 4 labs, which are much more intense, we're going to allow you a max of 2 grace days. And the reason we're doing this is because we don't want you to burn your grace. These grace days are valuable. They're critical, especially later in the semester when you're really, really busy. So we don't want you to burn up your grace days early in the semester. And this happens every semester. And then when Malik Lab comes up, there's no grace days left. And it's really sad to see that. And so we're going to limit you to 1 for those first 3. Just to help you, save you from yourself. Okay. Now, the nominal late penalty, if you don't have a grace day, is 15% per day. And we don't allow any hand-ins 3 days after the due date at all. So that Autolab shuts off, and then that's it. Now, if there's some kind of catastrophic event, then please contact us for an extension, right? So we're not, we try to be reasonable, but most of the most of the reasons that for requesting extensions, you can handle yourself using your grace days. And just, I mean, this is advice I give every semester too, but it's people often don't pay attention, but are just, they're unable to. But you for every one of these assignments, you want to start early. And the reason is you need to give yourself time to go seek help if you get stuck. Because the nature of these very programming intensive assignments like we have in 213 is that you're going to get stuck. And often it's very hard to bound the time you spend on some of these assignments. You know, it's not like problem sets where you can kind of predict, you know, this will take me like 3 hours to do these problem sets. For a lot of the 213 assignments, it's very difficult to sort of manage your time and bound your time. So for that reason, you really want to start early to give yourself a chance to get help when you get stuck. Now, in the lecture hall, you're permitted to have your laptops, but we ask you not to send email or instant messaging or cell phone texting or anything like that. If you're here, we want you to be attentive and engaged. Your presence in lectures and recitations is voluntary, so we don't take roll at either of those. We encourage you to come, but it's not required. And no recordings of any kind, except this one. Okay, the exams and labs are weighted equally, 50%. Midterm is 20, finals 30, and final grades are based on a straight 90, 80, 70 scale. Now, a rough outline of the semester. The first 3 labs cover programs, the machine representations of programs and data. Data lab is how we teach you about bit-level representations of data. So you'll solve a collection of puzzles in C. Like a puzzle might be is a little function that you have to implement, like absolute value. So a function that returns the absolute value of its input argument. The kicker is that we restrict the set of operators that you can use, and it has to be straight line code, no conditionals or loops. And so to solve these puzzles, so imagine how you might try to solve absolute value without using an if statement. Right? The normal way to do it would be if x less than 0, return x, or negative x. Right? See, I told you we make mistakes. Right? But imagine how you might do that without using conditionals and only using bit-level C operations. Right? So this is our way of teaching you how data is really represented in the machine. Now the BOM lab, which you probably heard at, this is kind of famous all over the world now, and at CMU. The BOM lab is the way we teach you how to read and understand assembly language. And a BOM, just briefly, a BOM is a C program that consists of a collection of 6 phases. And each phase wants you to type something in at the keyboard. If you type in what it wants you to type, what it expects you to type, then you've defused that phase, and it goes to the next phase. Then you have to type what that phase wants. And if you defuse all the phases, then you've defused the BOM. However, if you type in the wrong thing, then the BOM explodes by printing boom, and you have to try it again. And the kicker is, in either case, if you explode the BOM or defuse a phase, that information gets sent to AutoLab. And we use the diffusing string that your BOM sends us, and we check it out on a copy of your BOM that we keep on the server. Well, that's another thing. Everybody gets a different BOM, slightly different BOM. So we check. So when you diffuse a phase, AutoLab takes a string that your BOM sends us and then compares against the local copy of your BOM. If you explode phase, you lose half a point. So there's a real consequence to exploding your BOM. It's very, very tense. right? Until you learn how to use GDB to set a breakpoint before the function that sends the information to the server. And we want you to do that, right? So the bomb's really beautiful. It's kind of fun. It's kind of like a video game. It teaches you how to read compiler-generated code, because the kicker is we don't give you the source code. All we give you is the binary, hence the binary bomb. So in order to defuse a bomb, you've got to fire up GDB, single trace find where the code is for each phase, single trace through that code, and sort of reverse engineer it and figure out what it wants you to type in. And then you'll quickly find out where that function that explodes the bomb is, and you'll put a breakpoint there. Right? And so we want you to do that, because the bomb, besides teaching you how to program assembly language, it also teaches you sort of organically how to use GDB, because you really can't do it if you don't run GDB. And then the third lab is this is a new lab this semester that Randy's developed. It's called the Attack Lab, and we developed this lab specifically for 64-bit architecture. So this is a reflection of the change from 32 bits to 64 bits. And this is we're really excited about this one. You'll learn how to write exploits using return to a sort of a modern technique called return-oriented programming, which is kind of the modern way that hackers deal with the fact that stacks in newer machines move around and are prohibitive and make it impossible to execute code on the stack. So this is a brand new lab. I think it's really going to be neat. In the memory hierarchy, when we study the memory hierarchy, we have a lab called the Cache Lab, where you'll build your own cache simulator. So this is how you sort of learn how this hardware that Randy was mentioning called cache memory works. You'll build a simulator in C for that, and then you'll take a small transpose function, and you'll try to make that code run with as few misses as possible on your simulator. And this will involve sort of understanding of how the memory hierarchy works and how to exploit it. Okay. The part of the course where we sort of transition from hardware to interacting with the system software, the operating system, there's sort of a concept that we call exceptional control flow that exists in all parts of the system, and it sort of represents that intellectual transition from hardware to software. So this is how this was sort of a key idea that allowed us to kind of smoothly move from hardware to software in some intellectually consistent way. And so the ideas that you cover in exceptional control flow are like low-level hardware interrupts and exceptions, and then at the higher level, sort of involving hardware and operating system software, is the idea of a process context switch. Okay, so this is where you start to learn what processes are and how to ask the kernel to create and manage processes for you. At the next higher level are a software form of exceptional control flow called a signal. So this exists solely in the Linux kernel. And then even at a higher level, there's an application C language version of exceptional control flow called set jump and long jump. So this notion of exceptional control flow kind of exists in all parts of the system, and we cover it all at once. And the lab that we use to sort of exercise all these ideas is called the Shell Lab. And in the Shell Lab, you'll write your own Linux shell, which is really cool. So that's the program, the command line program that you interact with whenever you log into a Linux box. You're going to write your own. Okay. And I don't know, for me, that was really exciting when I could write something that looked like a real shell. It was pretty neat. The next area we'll study is called virtual memory. Virtual memory is a sort of combination of hardware and software that presents an abstraction to you of of memory as a very large array of bytes. When in reality, memory is a hierarchy of hardware and of cache memories and DRAMs. Virtual memory provides a very high-level abstraction as just a linear sequence of bytes. It also provides a lot of other useful abstractions that make many different parts of the system much easier to manage. Okay, so we'll learn about virtual memory. We'll learn how it works. We'll learn about the performance impact, potential performance impact that it has on your programs. And we'll also learn how to manage that large pool of memory that it makes available to you. And the lab that we do that, the lab where you'll do that is called Malloc Lab. And in the Malloc Lab, you'll write your own malloc and free functions. Okay, so you'll re-implement the functionality of the libc, malloc, and free. And this is maybe it's 2 pages of code, but I guarantee it'll be the most sophisticated, difficult 2 pages of code you've written. Not only because since it's managing the memory system, you can't use all of, C doesn't help you out a lot with abstractions for data structures. But when you're writing, but at least it does give you ideas like structs, unions that you can use to structure your memory. When you're writing a malloc package, you can't use any of those. You have to write exclusively on pointers and casting because the malloc package is working at such a low level. And so it's a very, very difficult piece of code for that reason, but also the design space for malloc is enormous. You have many options. They all have implications that trade off performance and memory efficiency. And finally, in the last part of the course, we deal with I/O, input-output. So far in the course, we've just talked about sort of running programs on machines. In the last part of the course, we'll talk about input and output, sending data into and out of the machine. So we'll look at basic concepts of Linux I/O. And since I think the most interesting form of I/O is networking, which allows you to talk to machines anywhere in the world using the internet, we'll learn how to do network programming. You'll learn how to write programs that use the sockets interface, which is the basic interface for the internet, to talk to machines, potentially any machine in the world. And that's really exciting. I can still remember when developing this course, I had 2 windows open on my machine. I was SSH'd into 2 different machines, and I wrote a program to send a message like hello world from one machine to the other. And when that hello world appeared on the second window, it was like so exciting. If you're a nerd, it's really exciting. But just the thought that could have been any machine, right? That could have been any machine. That it's just like opens up a whole new world. Okay, all of our hand-ins are using a system called Autolab, which was developed here, and you can access it. If you are on the roster as of this morning, if you go to the Autolab link, then you'll see this course listed on your page. If you're not enrolled, you won't have an Autolab account, and you have to be enrolled to get an Autolab account. So if you want to try to wait it out and wait for people to drop, I'll make the first at least the first assignment available from the course webpage, so you can work on it without actually handing into Autolab. But at least you can keep going. Okay, if you were enrolled, actually I didn't update this, but I updated the Autolab accounts today. Now, one final thing, if you have waitlist questions, please don't send email to the staff because we don't control the waitlist. So you should contact one of these, either Catherine or Zara, depending on which class you're in. Okay, so that's it. Welcome again. Looking forward to a great semester, and we'll see you on Thursday.